building envelope requirements of the 2019 Oregon Commercial Energy Code. I'm Connie Umphris, Communications Manager here at New Buildings Institute. Before we begin, I have a couple of housekeeping things to tell you about. First, you are muted and we cannot hear you. This helps keep the background noise down so that everyone can better hear the speakers. I want to direct you to the dashboard that you should be able to see on the right-hand side of your screen. If you are having technical difficulties and cannot see the slides or hear our speakers, you can use that question pane in this dashboard to let us know, and we will help you as we go. If we have time, we will take a few questions at the end of the presentation. Please ask questions in the same question pane. If there's not enough time at the end, we will follow up with a personal email. All registrants will receive an email tomorrow with links to the recording and slides for this session. Our speaker today is Sean Denniston, NBI Senior Project Manager. Sean's work at NBI includes analysis and review of data relative to commercial building energy performance and prediction, code and energy program effectiveness, and energy technologies. Sean uses his expertise for code analysis, tool development, and research. He also manages NBI's new construction program, which provides technical resources for new construction projects. Sean, over to you.
Thanks, Connie. So welcome everyone to today's discussion of the envelope requirements in ASHRAE 2016 as ASHRAE Standard 90.1 gets adopted for use in the Oregon Energy Code. Wanted to introduce you to New Buildings Institute. We are a nonprofit working to advance the energy efficiency of commercial, multifamily, and now even residential buildings. We work in a couple of different program areas, best practices and new and existing buildings. So this would be guidance, continuous code and policy innovation, and zero energy leadership and market development. Before we get to today's presentation, we want to thank the sponsors for this training, especially the Northwest Energy Efficiency Alliance and Energy Trust of Oregon with assistance from ClearResult. And we'd like to thank the Pacific Northwest National Lab and the Department of Energy for providing much of the content that we'll be using today for our training. Want to give a little bit of background for why we're seeing this transition to Standard 90.1 in Oregon's Energy Code. Oregon has some aggressive goals based in both legislation and executive orders for reducing greenhouse gas emissions and energy consumption throughout Oregon, and this includes, of course, what we consume through our buildings. In particular, in Executive Order 1720, we see commercial buildings specifically called out for meeting improved standards for energy efficiency. The Oregon Energy Code hasn't seen an update in a little while, and so the executive order sets goals for improvements for the Energy Code to really get up to at least where the national model codes are, which leads us to the transition that we're seeing now. ASHRAE 2016 is now going into effect, and we should see ASHRAE 2019 adopted next year. However, the direction that Oregon has gone, since we want to see not just national model codes, but maybe even better in Oregon, is to adopt what is being called a zero ready code. So this uses ASHRAE 90.1 as the basis, but also incorporates some additional features that have been created by the Architecture 2030 group. And it's a framework for estimating the energy consumption, but then what is the renewables that would be required for that building to make it a zero net energy building. This is based on Architecture 2030's zero code that leverages ASHRAE Standard 90.1 with renewables. The reason that what we have in Oregon is called a zero ready code and not a zero code like the pure version of what Architecture 2030 put forth is that the performance levels are the same, just like the zero code. We're looking at ASHRAE 90.1. But in Oregon, you won't have to actually install the renewable energy system. You'll just need to calculate how big that energy system needs to be. This will begin to give us a good idea of the kind of renewable energy systems that we will need to achieve zero net energy from buildings in Oregon. And to help you do that, Architecture 2030 actually has some tools available that we'll be leveraging in Oregon. enter some simple information about where the building is, number of stories, how it's used, and then some information about the sort of renewable energy system that might get installed these days. You know, you're looking at pretty standardized systems, and the information for these inputs are readily available. And this will actually calculate for you the size of renewable energy system that you would need for your buildings. For practitioners, this will be a great piece of information. It'll show them what the delta might be between what the consumption of their design actually is, and then what it would take to get it to zero net energy. And if they might need to do more efficiency in the future on these kinds of designs to get to a reasonably sized renewable energy system. Did want to point out one additional thing. Even though standard 90.1 is going to be the basis for the primary compliance path moving forward, the state has also adopted as a statewide alternate method that you can use IECC 2018 as your compliance path as well. So if you are more comfortable within the I-codes realm, the previous Oregon code is structured more like the IECC. So you will have that available to you. IECC 2018 is not exactly the same in stringency as ASHRAE 2016. On average, it's maybe just a little bit less stringent, but in individual cases, it varies by building types and by climate zones. So you'll have that available to you. Now, a lot of people will be familiar with 90.1 just because it is a commonly used energy standard. It's used in LEED and in many other programs and used for code compliance in many jurisdictions. But let's go ahead and take a look at how it's structured, because it's structured differently from how the Oregon code was structured before. We start with some fairly familiar things: purposes, scope, definitions, administration, and enforcement. But you can see that this is laid out in chapters, where then we get into building envelope, heating, ventilating and air conditioning, service water heating, a dedicated chapter for power, and then lighting and other equipment. You'll see then chapter 11 is the energy cost budget method. This is a computer modeling performance method for compliance. Then we have all the normative references, which are standard for pretty much any energy code. And then 90.1 has a series of normative appendices, and I think most people would be familiar with Appendix A. It gives the U factor for various assembly types and envelopes. So even if you've not been using 90.1, there's a good chance that you have referenced Appendix A to see what is the actual U factor of the assembly that you have put in your building, so that you can see where you fall for code compliance. And it also includes Appendix G, which is probably the other appendix that a lot of people are familiar with, which is a different path that's in 90.1 for modeling energy performance of buildings. Now, 90.1 has the same sort of scope that we've seen before in the Energy Code. It applies to new buildings and their systems. It applies to new portions of buildings and those systems, so additions. It applies to new systems and equipment in existing buildings, so alterations. And then any new equipment or building systems specifically identified in the standard, and it calls out what those are. And it gives criteria for determining compliance with the requirements. It's important to note that it doesn't apply to single family homes, and it doesn't apply to low-rise multifamily or multifamily 3 stories and lower. And it doesn't apply to any buildings that don't use any electricity or fossil fuels, which makes sense. It's an energy standard, so if you're not consuming energy in the building in these forms, then it wouldn't apply. As always, there are certain other buildings or elements that could be exempt in circumstances, either partially or fully. And of course, it doesn't circumvent any safety, health, or environmental requirements that we might find elsewhere in the building code. So if the building code tells you somewhere that you have to do something for safety, health, and environmental requirements, then what we're finding here in the Energy Code won't get you out of that requirement. You'll still need to do it. There are 3 primary compliance paths through 2016. One is the prescriptive, and then there's that chapter 11, the energy cost budget. And the third is Appendix G, which we mentioned before. In previous editions of 90.1, Appendix G was really just a rating system. It was used mostly in above code programs or to calculate percentage above code. It wasn't necessarily intended for code compliance, although it was allowed for code compliance in a lot of jurisdictions. With 2016, it is specifically identified as a code compliance alternative. And I want to call out with 2016 that there is a fairly substantial change to Appendix G. It's gone from the fairly simple compliance ratio equation that you see at the top of the performance cost index. It's very simple. You look at the proposed building performance, the baseline building performance, you compare the two, and you've got a ratio. But in 2016, what we're seeing is it's now setting a performance cost index target. And this is trying to calibrate where we are now with 2016 back to the performance level of 2004. And so it includes a bunch of building performance factors. So how much more efficient is 2016 than 2004? And the calculation gets more complex. We don't have time to really dig into this today, but I wanted you to be aware, if you are thinking of using Appendix G for compliance, that that system is different. You want to make sure that you take a close look and that you understand the ways that it is different moving forward. So when we look at the envelope, we have a couple of compliance options within the envelope chapter itself when we're looking at prescriptive compliance, when we're looking at compliance. So you have the pure prescriptive option, you have a trade-off option, an energy cost budget, this is chapter 11, or the performance rating method, so Appendix G. So we have those first two, the prescriptive, which is just simply do this, do this, do this. Trade-off is where you can trade off among parts of the building envelope, but you can't trade between the envelope and other systems. So you can't say, be more efficient in your envelope so that you can be less efficient with lighting, or less efficient in your envelope because you're more efficient with HVAC. If you want to trade off between systems, then you really need to do the energy cost budget or the performance rating method, either chapter 11 or Appendix G. Now, there are a couple of things about the way that spaces are regulated in 90.1. We have separate envelope component requirements for different types of conditioned spaces. So for non-residential, which are your standard commercial occupancies, office, retail, institutional. And then we have a set of requirements on the envelope for residential occupancies. So this would be high-rise multifamily, high-rise hotel, those group R occupancies. And then we also have requirements for a semi-heated space. And these are different envelope requirements for spaces that aren't conditioned the way that we condition for human occupation. So semi-heated spaces are heated, but they're not heated all the way up to comfort levels. So you might think of this is often happens in equipment rooms where you would heat just enough to make sure that you're not, bursting pipes or something like that. You want to just protect what's in the room, but you're not really making them comfortable for human habitation. And then semi-heated spaces can't be cooled. So a conditioned space, if it is a conditioned space, then it has a cooling system larger than 3.4 BTU per hour per square foot of floor area, or a heated space with a heating system output capacity larger than a table, and here's the part of the table that is relevant for Oregon climate zones, or an indirectly conditioned space. So if you're meeting these criteria, then you'll have to meet the conditioned space envelope requirements in the code. Within our mandatory measures, so the measures that will apply regardless of the compliance path, these are things that can't be traded off even if you are doing modeling. We have requirements for insulation rating and installation. Even though these are in 5.4, which is the mandatory section, it actually references 5.8, which exists largely for this purpose. We have a similar thing for windows, rating and installation requirements, how they get installed. This is where you would have the NFRC ratings and when those are applied to windows. And then one other mandatory measure, which is for infiltration. Now, The air leakage requirements in ASHRAE have a couple of different sections. There's a requirement for continuous air barrier, which should be fairly similar to users in Oregon. And then requirements for leakage from fenestration in doors, loading dock weather seals, and then vestibules. Now let's start with the air barrier. We have a whole series of prescriptive requirements for how the air barrier gets assembled. So these are, or actually you should consider these mandatory. These are kind of the minimum of how an air barrier needs to be constructed. So these areas have to be wrapped, sealed, caulked, gasketed, or taped. So these are the joints around fenestration and door frames. These are junctions between walls, so both walls between each other and foundation, building corners where they meet the roofs and the ceilings. Any place that you have a penetration of the envelope, any building assemblies that are used as ducts or plenums, which are limited, only a few places where you can actually do that, and any joint seams or connections between planes and other changes in continuous air barrier materials. So this is where you might have one air barrier material meeting a different one. You have to make sure that you seal those joints. So this is the basic conceptual framework for the air barrier installation. But we have a couple of options for how you actually demonstrate that you are complying with that. And there are three options. The first one is whole building testing. If you're building under 50,000 square feet, then you just test the whole building. And by testing the whole building, you can demonstrate that you have met the air barrier requirements. If you're a building larger than 50,000 square feet, so these are buildings where just testing the whole building might be challenging. You can still test the whole building if it turns out that that's going to work for you, but you can also do a certain amount of sampling, and the standard lays out the way that you do that, where you can test the building in sections and make sure that you've got representative sections throughout. So if you've got a larger building, make sure that you check the standard to see how that actually works out. Compliance is based on the results of the test. However, this is something that is new in 90.1 in the 2016 is looking at how this is actually structured. If your leakage rate is less than 0.4 CFM per square feet at 0.30 inches of water gauge, that's about 75 pascals, then you just pass. But recognizing that testing is probably new for a lot of commercial buildings. If you're greater than 0.4, but not greater than 0.6, then you can do a couple of remediation activities and still be considered meeting the requirement. So you have to perform a diagnostic evaluation on the building to see where the leaks are. So this is smoke tracer, infrared imaging. There's a whole series of ways that you can do this to identify the leaks. You have to perform a visual inspection of the air barrier and seal any leaks that you are able to identify, and then you have to submit a report to the code official showing that this is all the stuff we did and this is how we corrected everything. If you're over 0.60 though, you're going to have to work on the building, try to get it sealed. You might have, who knows what it's going to take. Hopefully you won't have to open things up, and then retest until you can at least get below that 0.60 and then show that you've done these remediation steps, or hopefully even get below that 0.40. Your second option is you could do a materials-based compliance. And this is very similar to what we've seen in the I-codes. And this just says you use materials with a certain air permeance, so less than 0.004 CFM per square foot under pressure differential. I'm sorry, that should be 0.0. No, that is right. And you have to test in accordance with the standard ATM E2178. Some materials are going to have these testing results for you, but the code also presents just certain materials that are deemed to have that permeance. And in some cases, the material has to be a certain thickness to be deemed to comply. In other cases, it just complies on its own. So you see things like plywood and OSB, insulation board, gypsum board can also be used, cement board, built-up roofing membranes, concrete. So all of these materials are deemed to have the right permeance, and you just need to make sure that you're sealing in between the different materials as we talked before. And then the third option is an assembly basis that you can actually mock up an assembly, whether that's your own assembly design from your building or an established assembly approach that has been tested in the past, and just make sure that it meets the requirement for an assembly. And here we see the 0.04 CFM per square foot again, and it's the same basic testing requirements that you would have for the same testing thresholds that you would have for whole building, but it's just for that assembly. And in a lot of cases, this is probably going to be prohibitive if you have to go get your assembly tested. But like I said, some assemblies have already been tested, and so you can just adopt one of those. Like with materials, we do have one case where the assembly is deemed to comply, and that's concrete masonry walls that meets these requirements. Either they're fully grouted or they're painted to fill the pores. So that's an assembly that is deemed to comply with this option. So you have these three options for demonstrating compliance with air barrier: testing, materials, and assemblies. So moving on, we have, beyond just the air barrier, we have some additional requirements for infiltration reduction. 5.4.3.3 is about cargo door weather seals. So, this is a pretty common thing that you see. You have cargo doors so that when they are closed, you get a good tight seal on them. This is going to be especially important in any time that you have a conditioned warehouse situation. And then there are some requirements for vestibules, and these get fairly detailed. So in Oregon's climate zone, vestibules are required on entrance doors that are to conditioned spaces that are over 1,000 square feet. And the code defines what that actually means. So not all doors to the outside are considered entrance doors. However, it also requires vestibules on any door from conditioned space to the exterior that opens to a space that's greater than 3,000 square feet. And then this vestibule, and we see a couple of diagrams there on the right, we have requirements that the vestibules themselves need to meet. So you have to have a vestibule, and then the vestibule needs to have these characteristics. It has to have self-closing doors. This isn't automatic doors. These are self-closing doors. So when you let them go, they close themselves. The interior and exterior doors should not be open at the same time. The distance between the interior and exterior doors has to be less than 7 feet when in a closed position, or not greater than 7 feet when in, no, not less than 7 feet, I apologize. The distance between the interior and exterior doors cannot be less than 7 feet when they are in their closed position, so you don't have to worry about door swing and the impact that'll have on the dimension. The floor area of the vestibule can't be greater than 50 square feet or 2% of the gross conditioned floor area for that level of the building. And then the exterior envelope of the vestibule, if it's conditioned, has to comply with the conditioned space envelope requirements. And if it's unconditioned, then it has to comply with the semi-heated space requirements. The idea being that even though it might not be conditioned, it's picking up conditioned air when the door to the conditioned space gets opened. And then we have some specific vestibule requirements for, really we're thinking of retail spaces here. This is the primary area that this is going to apply. That any time that you have an opening into a space greater than 40,000 square feet, then when the doors are opening in and out of the vestibule are equipped with automatic, electrically driven, self-closing devices, so automatic doors, the interior and the exterior doors shall be at least 16 feet apart. So really think about your retail spaces. Before we had a minimum of the door spacing had to be 7 feet. Well, if you're going to use automatic doors and you're opening into one of these big retail spaces, then it's got to be 16 feet apart. There are, of course, exceptions. Always we have exceptions in the code. So non-entrance doors, of course, don't have to meet that 1,000 threshold, only the 3,000 in the Oregon climate zones. And anything opening from a dwelling unit. Any building entrances with revolving doors don't have to meet the vestibule requirements. And then entrances into semi-heated spaces, and enclosed elevator lobbies for building entrances directly from parking garages. So some very specific situations here. One thing I did not mention earlier, for those of you who might be familiar with 2010 or 2013 ASHRAE, we've tried to identify throughout this when a requirement is different in 2016 from what we had previously. So any place that you see red, that means that we're looking at a requirement that is different from what was in ASHRAE before. So let's look at the actual prescriptive requirements if you're going to take the prescriptive path through and what you would need to do for your envelope. Here are the Oregon opaque envelope requirements that were in place previously. So you can see the general level of requirements from the roofs, the walls, the slabs, and this should look very familiar to you all. So here are the envelope requirements that will apply in Oregon under 90.1 2016. You will see in a lot of cases, we are looking at more stringent envelope requirements. You'll see that we have a little bit of different categories in a couple of places. As if you have an actual 90.1 book, one of the advantages to the way that ASHRAE is actually put together is that they group all of the requirements for a climate zone together in one table, so you're only looking at one table rather than in the previous code where you had to look at different tables and then find your climate zone. And here's just for climate zone 5 in this case. So roofs, walls above grade. And now for the rest of the tables, here's climate zone 4 again. And 5. So in ASHRAE, we are definitely seeing an uptick in the envelope requirements in a lot of places, but we're still not to, levels of very stringent that we're seeing in some of the above code proposals and green codes. So let's also take a look at what is in the code, the previous Oregon code for fenestration. And what you will see in ASHRAE moving forward. And again, we're seeing not a big increase in stringency, but we're certainly seeing an increase in stringency in many cases. Now, one thing I do want to point out is that the categories are just slightly different and the approach to the windows are just slightly different. So make sure that you're looking at that. And here's for climate zone 5. Now in the prescriptive path, we have requirements for the actual, the performance of the windows, but we also have limits for the vertical fenestration area. So it can't be more than 40% window to wall ratio for your vertical fenestration. If you want to have more than 40%, then you're going to have to use an option besides the prescriptive option. There are some exceptions built in there for street level vertical fenestration. These are kind of retail spaces. And then your total skylight area has to be less than 3% of the roof area, but you can go up to 6% if you have automatic daylight controls for the lighting that is under those skylights. And there is additionally a requirement that not only, this might seem a little bit strange, there's a maximum amount of skylights that you can have, but you have to have skylights in some circumstances. So in certain enclosed spaces, skylights with the associated automatic daylight controls are actually required. So the space needs to be greater than 2,500 square feet. The ceiling height has to be greater than 15 feet, and then only in these specific office types: office, lobby, atrium, concourse, corridor. And you can see the list here. This is probably going to mostly find application in kind of your big box retail situations, but this will also apply to a fair number of offices, especially your single story offices and a lot of single story developments may trigger this. And then for windows, we had a set of SHGC requirements earlier, solar heat gain coefficient. And ASHRAE allows for adjustments to the SHGC based on projection factor of permanently installed overhangs. And really this is taking into account that the overhang is providing shading to the window, so it's not as critical that the window itself have a good solar heat gain coefficient. And the projection factor is really just how far the overhang projects beyond the window, divided by how high the overhang is above the window sill. So here we've got a couple of examples of how that might look. And then we have a table. And so based on what your projection factor actually is, you can see those on the left, then you can see the SHGC multiplier for the south, east, and west orientation. So the more overhang that you have, then the more you get to reduce the solar heat gain coefficient. Notice, you won't be in a situation where that requirement is eliminated, it's just reduced. Another thing that you'll notice here is that it is for south, east, and west orientations, and that's because ASHRAE has different SHGC requirements for north-facing windows, which makes quite a bit of sense. Now, let's go ahead and talk about the trade-off option that we have in the code. So we've gone through, here's prescriptive is everything just matches, these tables and these requirements, and just do everything that's in there. You don't have to go to full modeling if you want to actually begin to trade off. And in fact, if within ASHRAE, you can go above 40% window to wall ratio using the trade-off option. One of the main ways that we see to do this, of course, ComCheck makes it very simple, a way to demonstrate what the trade-offs are between window and wall to increase, to vary these things. However, you could conceivably use just computer software and not do full modeling. You could just model the envelope itself and use that to demonstrate your trade-off as well. So you've got a couple of options to do so. Really the big advantage of this is that it lets you do a weighted U-factor approach for your whole envelope. And probably the most common reason that you would be doing this is because maybe you have just part of your assembly that needs to go below the code requirements because you've got a specific or peculiar situation, or maybe you have a couple of windows that need to drop below the code requirements for the same thing. Maybe it's a decorative window, or maybe it's just a peculiar for some reason, or maybe it's not NFRC rated when it otherwise would need to be. And for those simple things, then ComCheck really is a pretty useful tool to help you just do that trade-off to get more efficiency elsewhere in your envelope. If you want to do something more sophisticated, then you might look at modeling. Design teams are going to make that decision of whether it makes sense to just model their envelope and not go ahead and model the whole building, but they may have a reason to do so. We do want to spend just a little bit of time before we close for questions, looking at scope and application and how these are applied to, not just new constructions. Pretty straightforward for new construction and additions, of course. So any additions to the building basically have to comply with all the opaque envelope and glazing requirements for new construction. It's almost as if it is, well, it is as if it's a new building just built up and attached to the existing building. Alterations are a different matter. In alterations, it's only when you actually impact and really open up the wall or replace the windows that you have to comply with the requirements as if they're new construction. So this is going to happen if you have if you're gutting part of a building as part of an alteration. If you're replacing windows, those windows would need to meet the requirements for new construction. If you are doing a gut rehab, then then you will have to bring the insulation up. There are some caveats built into 90.1 for technical feasibility. You know, if you've got, say, a wall assembly that just it doesn't have the depth to get the insulation that you need, there are some limitations built into it. And then the 90.1 identifies some specific circumstances where you don't actually have to meet the new construction requirements. So these are specific alterations that are called out as just being different. So storm windows kind of makes a lot of sense. You're actually just putting a window on the window. If you're fixing a window rather than replacing it, so you're just replacing the glazing in the sash and frame, then you don't have to meet the new requirements. This could be a really big thing. It'd be horrible if you had a broken window, and that means that you have to replace the whole window unit. Certain alterations to the roof and wall and floor cavities. If you're doing a roof recovering, so this is where you're just putting a new roof on top of the old roof, or if you are just taking the roof off, so just the roof covering itself and putting a new one on. If the roof is insulated integral or below the roof deck, so it's a little bit more specific if you're doing roof replacement. Of course, you won't have to come back through and do vestibule retrofits, and as long as you are doing, if you are doing a window replacement, if 25% of the existing fenestration with the same or better than what you had in place before. So you have these sets of specific things. I think alterations are probably where applying the code is gets the trickiest. I will say one thing about alterations. If you're facing a difficult alteration situation, you might think about using the IECC path, because the IECC has actually restructured the way that it is put together. And this is something unlike what we had in Oregon before, to pay very close attention to how the code is applied to existing buildings. And so it breaks out in more detail how the requirements apply to additions and alterations and changes of occupancy and historic buildings. And so there's some more clarity there, and that might end up being a useful thing for you to consider as you are doing alterations on existing buildings, that the IECC may provide some greater clarity for you, and it's an option that's available to you. So we actually went through that a little bit quickly, so we do have some good time for questions. So Connie, do we have any questions on the line?
None have come in yet.
Well, we'll give people a couple of minutes to enter in any questions that they might have. And, you know, I think when it comes to the envelope, the thing that people always wonder about the most is those actual envelope requirements. So I'm gonna go ahead and put those up so that people can get another look at them. One of the things that you will notice here is that while continuous insulation is not always required to comply with these requirements, you will see a lot of circumstances where continuous insulation is the most logical path to compliance.
Okay, Sean, we have had a question come in, actually a couple.
All right.
I will address the first one. Will this material be sent out after the presentation? Yes, tomorrow you will receive a follow-up email with this PDF of this presentation, as well as a link to the on-demand recording. So to the other questions, under minimum skylight fenestration area, could translucent wall panels meet this requirement in the case of metal buildings?
So that is going to come down specifically to the specifications of the wall panels that you have being installed. So for meeting the 3% minimum, there are minimum requirements for the skylights that meet that requirement. And so you'll need to check the requirement that's actually in the code, and I'm paging through my own copy here. But the big thing is you're going to need to check the specifications of your translucent wall panel to make sure that it meets the requirements that are acceptable in the code. So yeah, so the biggest thing that you may have an issue with is that the skylights have a minimum haze value requirement of 90%. And those wall panels that are used in metal buildings, a lot of times they haven't been tested to the testing standard that skylights are tested to. And even if they have, they may not have the haze factor that you need to comply with that skylight requirement. So that's going to be really the big thing that may keep them from being able to be used. Beyond just, in metal buildings, the practical issues aren't as big just because of the way a metal building is put together. But the big one is going to be that it meets that haze factor requirement.
Okay. Did you mention something about WWR allowances if DL controls are implemented?
So this is one of the big differences between ASHRAE and the IECC is the IECC has a lower window to wall ratio threshold than ASHRAE does. It only allows for 30% window to wall ratio, but you can go up to 40 if you have a certain percentage of the building in the daylit zone with daylighting controls. In ASHRAE, it's just 40%. So there isn't this additional area that you can get for window to wall ratio for daylit zones. However, you can get more skylight area, up to 6% as opposed to the 3%, as long as you put the lighting under the skylit area, as long as they are provided with automatic daylighting controls. So not window to wall ratio, but skylight to roof ratio, you can get an increase under ASHRAE. This is one of the bigger differences between IECC and ASHRAE, really when you're looking at the envelope requirements, is the different approach to window to wall ratio.
Okay. How does ComCheck address thermal bridges? Do the U values include a factor for thermal bridging, say from metal Z-furring through exterior insulation?
Mm-hmm. So this is one of the weaknesses that's in the code right now, is that it really doesn't do very much to address thermal bridging. One of the ways that you would use ComCheck is by putting in assembly values. And if you go to Appendix A, that's where you have the U factor values for a whole bunch of different assemblies. And those values take into account how an assembly is put together, how concentrated are the structural members, what are they made out of, is it steel or is it wood? And it accounts for the impact just on the weighted U factor of these, what are effectively thermal bridges, but it doesn't account for the true impact of thermal bridges, like say, the passive house, I know what the symbol looks like, but chi or chi value does. And so what we have really in ASHRAE and in IECC, none of them really fully account for the impact of thermal bridges. And so you won't be seeing that in the U factor calculation beyond just what you get from calculating an assembly as it is. This is something that they tried to address in ASHRAE 2019, but the approach turned out to be so complex that it was too complex to implement in the standard itself. So hopefully, from an energy standpoint, we'll see the codes better addressing thermal bridges in the future. But right now, things like that specific circumstance, that's one of the big ones. Another one is, the hangers for cladding systems. Those really aren't accounted for in the envelope requirements.
Okay, normally for code questions, we contact the BCD for clarification. Who are we supposed to contact with ASHRAE for questions or clarifications?
So it's still going to be the BCD. Even though the code is produced by ASHRAE, when it gets adopted by Oregon, we saw one big difference is the renewable energy part. They made some modifications to it. In this case, very minor modifications. They wanted to leverage these national tools that are available. But when it comes down to how the code gets interpreted, it is still the BCD. They will say what these requirements mean, what it means, how it gets applied to your specific situation. So in that case, it really hasn't changed. And in fact, most of your code process is going to be largely the same. Your submittal process, your inspection process, most of that is going to stay the same. Really, the only thing that the shift to an ASHRAE standard does in Oregon is it shifts the requirements that are being enforced. But interpretation, all of that, that's still going to be through BCD.
Okay, for wood construction, if continuous insulation is required in prescriptive approach, is there an exception similar to the old code?
So there's two ways to look at this. In our envelope tables, and it would be useful, why don't we just go ahead and go to one of those tables. Let's get to the above grade. So here we are, walls above grade. And what you see here is we have, if you go to wood framed and other, you have R13, that's the cavity insulation, plus R7.5 continuous insulation, or R19, so more cavity insulation and less continuous insulation. Now, there isn't just an outright exception. You can use Appendix A or another assembly, weighted U factor to try to put together an assembly that is still wood framed and is all cavity insulation, through using different framing techniques, through using different, better cavity insulation. You might be able to hit that assembly U factor that you need to hit without doing continuous insulation, or maybe by doing less continuous insulation, but there isn't just an exception built in. Really, you can almost think about it as the U factor is the requirement. You have to meet that U factor in your assembly, and the code gives you some very common examples of how you would do that with a combination of cavity and continuous insulation in, a wood framed or a steel framed or a metal building or a mass wall. But really, what you need to hit is that U factor. So if you can't do it with the R values that are in the table, you'll really have to find a different assembly that you can put together to meet it. Or, you can go through the modeling approach where you can make up what you're not achieving with your envelope through more efficient lighting or more efficient HVAC systems.
Okay, so far this is the last question. Please expand on slab edge insulation requirements.
Let's go ahead and go to slab edge. All right, so slab edge is that F factor requirement, and it's unlike U, it's unlike C, it's a per linear foot. And here we have what the insulation minimum R value for insulation if you're just going to go around the perimeter of your slab. So you can see here R15 for 24 inches below, and this is really meant to keep the heat that goes through the slab into the ground, at least contained in the ground underneath the slab, so that it's not spreading out to the ground around the building, especially the ground that's exposed to the exterior. So that's R15 that needs to go to 24 inches below. Let's see in climate zone 5. Yeah, so if you have a heated slab in climate zone 5 in Oregon, then you actually need to go deeper on your slab edge insulation. And this is really just meant to keep the heat in the slab under the ground, under the building, so that the heat losses through the slab are not as significant. Keep in mind that you are not required to insulate all the way under the slab, which is something that you might see in some states and some other standards.
Okay, no other questions have come in.
All right. Well, thank you everyone for joining us today. We covered HVAC yesterday, and in about half an hour, we're going to be talking about lighting. This is going to be a shift for a lot of people, moving from what Oregon had before, which was more of it was a little bit home brewed, but it was probably more like the IECC than ASHRAE. But the ASHRAE is a well-supported standard with lots of resources out there to help you understand it, and it's a rather well organized standard, so it should be pretty easy to understand if you are familiar with reading code language. If you do have questions, make sure that you ask your building official. It's better to ask earlier if you have any kind of confusion than to have an unpleasant surprise later in the development process. And once again, thank you for joining us today. I hope some of you will be joining us for our lighting session later on. And of course, the recording will be available if you want to review anything or look through the presentation to remind yourself. And we'll see some of you soon. Thank you.